Hello, it's me, Mr. Cho, and yeah, we're just going to continue on from where we left off. So in the previous lesson, we learned about this thing called qualitative data, which are things like all of this, even the drawing, all of these are under qualitative data. And now let's talk about this thing called quantitative data, right? So what is quantitative data? Is data in a numerical format. Anything to do with size, length, breadth, area, volume, values such as pH values from 0 to 14. All of these are quantitative data. So quantity, right? Think about it as in a number. I get a certain number from a quantity. Okay, that one is very obvious. So we will now talk about how to present in tables and graphs. Okay, so first of all, you need to be aware of these two types of variables. The first variable is called independent variable. This is the variable that is changed. Okay, so let's say for example, I want to measure, right? That's the meeting, okay, let's say I want to measure the height at which equal plants, right, will grow when exposed to different amount of sunlight. Okay, so what is the thing that I'm changing? I'm changing the amount of sunlight or light. Okay, so that is my independent variable. Okay, I think in lower sec you may have learned it as the word change variable. I guess that is easier to understand, but yeah, sorry, need to write independent now lor. Okay, you're older, more independent, so yeah. Okay, if you cannot remember these two independent and dependent things, right, just think about yourself. Like when you become independent from your parents, right, then you change yourself, like you change your looks lah, your clothing lah, all that kind of thing. So now you're very independent. Okay, but if you are dependent, like your parents always tell you to do, they will measure you, they will like control you, so that's called dependent, right? So that's what's being measured. Okay, so back to the example of the plant that I was talking about. If I change the amount of light, how tall will the plant grow? So what am I measuring? I'm measuring the height of the plant. That is called a dependent variable. Okay, there's also one thing called the constant variable, okay, which you also need to be aware of. Constant variable means what else must you keep constant? Okay, so in my example of a plant, what must you keep constant? There's three factors for photosynthesis, right? Light, water, and carbon dioxide. So you must keep the other two factors for photosynthesis constant. That means that the amount of water all the plants receive must be the same, and the amount of carbon dioxide that all the other plants receive must be the same also. Okay, so that will allow for a fair and reliable test. Okay, so when you do the experiment, you are writing down the data, you get some qualitative and quantitative measurements. Then you need to present your data in a clear format. So the best way is to learn how to record data in a table. So before you draw a table, just plan a bit. Plan your table first. Don't just go and rush and then you end up having to erase everything and then redo. Okay, or worse is cause you have to do it in pen. So yeah, you have to use your cancel and find another area to draw. So they are not so good. Okay, so plan first. Table must be easy to read. Okay, the columns in the table must have a heading stating the variable that is measured with the SI units. Okay, so for example, like I said just now, the plant, right, amount of sunlight. Okay, that one you can maybe amount of sunlight slash units. Then height will be also slash cm. Okay, that'll be the units, the SI units there. Okay, then if there's a need to repeat experiments, then it's important to group the measurements together so that the average or mean of the measurements can be calculated. Okay, these two words, they are very similar. Average is sometimes called mean is sometimes called average. There's slight difference, whether it's used in math or in statistics or something like that lah. Okay, but basically they mean the same, similar enough lah to mean the same thing. Okay, lastly, record the units of the quantity only in the headings. Okay, so I'll show you what I mean in this picture here. Okay, so like that. Alright, let's say for example you're doing osmosis and you got a change in length of particle strips in different salt concentrations. 3 readings are taken for each salt concentration. Okay, so what is this concentration? Okay, now this one is molar, right, /dm cube. This is usually given to you. But sometimes you need to make your own, maybe a percentage based kind of solution. So I put like maybe 5% solution, 10% solution, 15% solution, 20% solution, which means that in 100 cm cube of water, 5 gram of it will be salt. Okay, so I put the salt, then I top it up to water with water, and then I stir all the way. Okay, that's called percentage base. But if sometimes they also give molar base. Okay, molar base you will not learn how to count until you learn chemistry. You count all this thing called molar. It's actually not easy. Okay, but it's actually also quite fun. Okay, this dm cube is another way of saying liters. Okay, I know there's a lot of ways of saying liters. Anyway, so for example, you have the table, right? You start with all your headings. Your independent variable, which is also what you might know as your change variable, is always the first column. Okay, so your concentration of the salt solution should be here. And then, because you are potato strips, right? You got 3 potato strips, so you make one line for each of them. Potato strip 1, 2, 3, 1, 2, 3, 1, 2, 3. Because there's 3 different solutions here. Then you need your initial length of your potato strip in a certain unit. It could be in cm, it could be in mm. Just make sure you read the question and you write down what the thing is properly. Okay, then after that, the dependent variables are recorded here. So these are your dependent variables. The initial and final length are your dependent variables. And the change length also is a dependent variable. Okay, so your final length. So for example, you put your potato into 0.2 of this salt solution, and let's say you started at 60, not 60, but because it's cm, 6 cm, right? So it should all be you should all start the same, right? So it'll be like 6 cm, 6 cm, 6 cm, all this whole line is 6 cm. Okay, and then after that, the final length will maybe be 6.1, 6.2, and then this one will be maybe 6.0. Okay, so no change. Then you calculate the change in the length. Make sure for this change in length, you better put the plus or minus there. Okay, so why? Because if it's a positive change, it's a positive. If it's a negative change, then it's a negative symbol. Okay, so if let's say for example, over here, my initial length is 6 cm, right? And then somehow the potato shrink because of the some very low water potential, right? This solution very low water potential. So my potato start to shrink, shrivel up, right? Become flaccid. And so the change in length was maybe minus 0.5 cm. Okay, so I must write that minus in front of it. Same for the positive, also must write that plus in front of it. Okay, then let's talk about average change. Okay, average change or mean change, you just take the 3 numbers here, these 3 numbers, and then you write in the box. A bit funny lah. By right, these 3 boxes should be combined together, so you don't actually need this line. These 2 lines are a bit zoteng. Okay, so actually you don't need these 2. Just write one big box here, similar to this, right? Similar to this, and then you do the calculation, your math. You must write the working. So this one plus this one plus this one, right here, right? Plus together, and then divide, and then divide by 3 equals to your number. Okay, don't need to put units. Okay, none of these need to put units. None of these need to put units in. That means don't need write 6 cm here. Why? Because here already have. Okay, so all this area here, all don't need units. As long as the top here got unit, it covers all the thing below it. Okay, so if here is cm, it covers below. Same for this side. Don't need to write more per dm cube here already, because here already cover for this 3. So don't repeat yourself. Okay, so yeah, right, we are in this experiment, we change the different concentration of a solution to find out the effect that it has on the length of potato strip. In this particular experiment, the concentration of the solution is an independent variable, while the length of the potato strip is a dependent variable. Okay, so that means that I change the concentration of the solutions, 0.2 to 0.6. And then the length of the potato strip also changes because of the change variable, that independent variable. So the length of potato strip is the dependent variable. It was measured. I used a ruler. I measured this potato strip, so it's called dependent variable. Okay, so now we need to process a data by doing certain things to it. Okay, most likely we'll be plotting graph. For sure, there will be a graph question in your O level. Okay, every year we'll have at least one graph, either bar graph or line graph. Okay, so either, or sometimes even both. Sometimes it could be bar graph and line graph. Okay, they love their graphs. Okay, so we start. There's 4 or 5 things to know about graphs. Firstly, clearly labeled axis with appropriate units. Oh, sorry, miss out one part here. The size of the graph first. A good graph should be large enough. Same thing, 2/3 of the graph paper, or to be safe, round up 70%. Okay, and it should include clearly labeled axis with appropriate units. Okay, so what do they mean by clearly labeled axis? This is your clearly labeled axis. There's 2 you need to label. Your y-axis, your y is going up and down, and then the x-axis, which is going from left to right. Okay, so you see, where did they get this wording from? You literally copy it out from your table. So whatever you wrote on the table, like for example here, right, this is something, whatever you wrote there is what you should be writing over here. Same thing for this, change image. Okay, this is not the same as this, so that's why it's a bit of change, but it's something similar. For example, if I want to write for this table, I'll write concentration of salt solution /mole /dm cube and paste it here, and take this one, average change in length /cm, and paste it here. Okay, so actually very simple, just copy and paste only. Okay, and like I said, the x-axis is your independent variable, so this is just like what we see here, the concentration of the salt solution, and then the y-axis is the dependent variable, the change in the mass. Okay, take note, sometimes you can do negative, okay, but not all. Sometimes you don't need. So for example, if you realize that your potato, right, the potato strips, it start to some of the potato strips actually reduce in the change in the mass, reduce, it lost mass, then you must have these negative numbers over here. Okay, so choose an appropriate scale. For example, 5 squares is 1 unit. Okay, so like that, right? 5 squares is certain amount of units. Oh, sorry, not 1 unit. 5 squares is 2 units. Okay, so like that, minus 0.6, minus 0.4, etc., etc. For the y-axis, for x-axis, same, right? Like that. Okay, take note, your 0, you should start from 0 for both x and y. Sometimes you will not have such nice things. You see like what nicely, 2, 4, 6, 8, 10, everything all in 2s for you, right? Very nice. What if they only give you three things like this, 0.2, 0.4, 0.6? How to space out? Okay, then you just space out across the whole thing. So 0.2 will be somewhere here, 0.4 will be somewhere here, 0.6 away. So you need to space out everything. Okay, or if you're 0, then you start here, 0, then the middle one, then the last one over here. So really make sure it's all spaced out. One last thing, sometimes also you may even get this one as not equal. So maybe it's like here is 0.2, then here is 1, then here is 10. Okay, so like some very funny numbers, very weird. Sorry, no choice. You need to figure out a way to spread it across, but it must follow the scale properly. So that means like if it's really 0.2, then you really want small line over here, then the big number will be like very far away. So it'll be like, from short and medium, it's like boom, very very far away. Okay, so yeah, that kind of weird. The scale has to follow the number, that's what I'm saying. Okay, so yeah, that's what. Okay, using how to draw the plots, must be axes, no dots, no circle, no other triangle, whatever, just a cross, simple cross. Make sure it's big enough to be seen, but not so big that it will cover other boxes. So you see, it's usually about the size, equal to the size of that square. Okay, but if you realize that your handwriting is very small, very faint, please use a darker pencil to really make sure that it can be seen. Okay, same thing for your line. Your line will be drawn with a ruler, and this is what you call as a best fit line. Now you notice, right, this line is a best fit. It's not actually cutting through every single dot or every single plot. It's actually going through like an average of the plots. Okay, I will explain more about this in the next page. Okay, but before we get there, let's talk about this. Okay, so just remember these 5 things. Big graph, clearly labeled axis with appropriate units, suitable scale on both axes that can be easily read off the graph, usually in multiples of 1, 2, 5, or 3. Avoid weird scales, like don't put 3, 6, 9, 12, 15, that kind of weird numbers. Then a title, I forgot to mention that. Okay, title. Okay, then there might not be marks given for it, but just put. Okay, then clearly plotted points using cross. No, I don't see why they put a circle dot. No. Just use cross only. Okay. And then okay, I see what they're trying to say. If more than one set of data is being plotted, then you must use a different symbol to plot and provide a key or legend. I've never seen this happen before. But if really that's the case, then that's why there's a dot. It's a backup. But I don't think it happen. Okay, and then a fifth, or rather actually it's a sixth, because of this they didn't put large enough as 1 point. The sixth is your best fit line or curve. After you plot all the points, you draw a best fit line or curve, and this line curve can be help determine the trend and make predictions. Okay, let's talk more about this best fit line. It's a bit tricky to understand. What is a best fit line or curve? Okay, so this is a line, this is a curve. So there should be approximately the same number of data points on each side of the line. Now you see, this, you'll be very tempted to draw roller coaster, like, wow, you go like that, then you go like that, then you go like that, then you go like that. Okay, it looks very nice, right? Why you got to connect all the dots, like playing those primary school connect the dot game. No, right? We don't do that really for science. We just connect, right? Average out. You try and see equal, one on the top, one on the bottom, roughly about there, and draw through the line. Okay. The data points should be evenly distributed above and below your best fit curve or line. Your curve or line should have the smallest average distance from each of the data points. Okay, so try to really put it in the middle. Note that in some cases, the best fit line do not pass through any of the data points, right? So this is why it calls best fit. It never asks you to fit, okay? Just best fit. And your line should not be extrapolated beyond the data points. Okay, what does that mean? So you see here, the cross ends here, right? How come here got extra? How you know this? Same thing for this. The plot is here, ends here. How you know this? You got do 0, man? Right? You don't know. Okay, don't go and draw longer than the last and the the first and the last plots. Okay, so let's look at some examples. This is a line, so I draw best fit line. Very simple. Okay, tick. This is a curve. I draw my best fit curve. Best fit curve, you may need to practice a bit. Okay, try to go and draw some curves properly with your hand. Don't be shaky and then your curve like wobbly. Just, straighten your hand, focus, shoot, make a nice curve. Okay, it does take a bit of practice, so just go and draw curves in your foolscap paper whenever you're free. Okay, so bad examples. This kind of weird scale, 0, 3, 6, 9. Okay, your scale should be in either 5s or 2s or 10s. So don't do this kind of scale. And you see the line is not in the average. It's not in the middle. There's 3 on the bottom and 2 on it. So there's none on the top. It should just be a little bit lower than the average out. Okay, and the line should not be drawn beyond the plotted point. So don't have this kind of extra tail or extra head over here. Okay, then let's see the scale for the x-axis is not appropriate, resulting in a small graph. Okay, so even though this is the best fit, yes, some is on the left, some is on the right, left and right, then it's too small. It's only focused on this whole section over here. What happened to all this space? Right, it's a waste of space. Okay, you need to fill up at least 70% of the space. So this you should just remove this 20 to 50, spread out this 10, become like 1, 2, 3, all the way to 10 at the end, and then spread it out nicely so that it fills up the space. Okay, let's look at more bad example. The points are crowded at one corner of the graph paper due to inappropriate scale for the x-axis. Okay, so same thing. This one over here a bit weird. Okay, then you'll be like, but I must put 5, 10, 15, 20 ma, right? Then what can I do? Okay, this one later when I go to class, I'll teach you a special trick. Okay, how to start on a different number. Okay, anyway, over here, this one also. Okay, this is not a best fit. This one is roller coaster. Okay, you roll like that and go all the way up. Anyway, don't need to connect until like that. So funny. Right? Just draw a best fit, something like that. And through, doesn't have to touch every single plot, just average out the plots. Okay, starting from the start and end, don't extrapolate out. Okay, That is what I call as a best fit line or curve. Now we're going to talk about plotting a histogram. Okay, histogram, simple word, bar chart. Okay, so for your histogram or bar graph, the x-axis is the variable being measured, whereas the y-axis is the frequency of the variable. So for example, if there's a group of students with different heights, some of them are shorter, some of them are taller, etc. Okay, so I think bar graph, I mean, you've been doing it since primary school, shouldn't be a problem. Just that, just be aware lah. Okay, so for example, in this case, it's a range. So the range will start like that, and there's this scales of the x-axis. Remember, label your axes. So your height / m must have the m also. You got it from here. And the frequency, okay, frequency no unit lah, so frequency is frequency. But if there's unit, then put a unit there also. Okay, your bar graph don't need so like you don't need to be this one is 6 is a good number. If you make it like 10 then your bar graph very short, very small. Same thing lah. Remember, 70% of the graph. So just choose an appropriate scale of this. I prefer, if there is space on the graph, I prefer if you actually space out. Okay, in this case you can't space out because this is a 0.5 to 0.8, so it's a range. But if it's like separate things, so like maybe it's like A, B, C, D, E, F, G, right? Then I prefer you to give a bit of spacing for all these graphs over here. That means like there should be an equal space, so this one should move to the right, this one should move further to the right, and then everything's nicely spaced out. Okay, but it depends on what is the x-axis scale. Okay, let's zoom past this. You pause the video, you read it yourself. I don't want to say. Anyway, very simple, just read it. I honestly have never seen this being tested, but just know this. Maybe your math might test you. I don't know. Okay, same for gradient of a curve. y2 minus y1 divided by x2 minus x1. So that's the gradient of the curve. Okay, let's talk about calculation of mean. So remember I said mean is something similar to average. Okay, why do we do the taking an average? Highlight this sentence. You need to take an average to reduce error and give a more reliable result. Okay, most of the time average and mean have the same meaning. So how do we do that? You just sum up all the observations, right? So remember our example of osmosis, the potato, you add up all the different length or the different mass or whatever, and then you divide by the number of observations. So very simple. Okay, sometimes you may get what you call as an abnormality or anomalous result. And what you should do first of all is you need to repeat that particular experiment. So let's say you got some weird result here, you should try and redo this one, see whether you can get it further down. Okay, if you really cannot, if it's really different, as what it calls a true abnormality, right? Then maybe the sample was contaminated. That's one possibility, or maybe it really just is like that. Maybe it really there's something like that. So we don't know. Science is unknown, a lot of unknown, right? So just draw it there, like what you see it, and then continue with your best fit. Because majority of the points are at the bottom, right? You don't need to go in special case for this guy, go all the way up like V shape. No need, or N shape. Just ignore him, let him go and emo one corner, and then the rest of the friends all connect out. Okay. Okay. Yeah, like I said, if only one or two values are very different, ignore them, and also do not use them in calculations. Okay, but ideally you don't get this kind of thing Okay, because this kind of thing maybe it means that something a bit messed up already. Okay, now the last skill, or the second last skill actually, is called planning investigation. This is very difficult, very tricky, but if you can do it properly, right, this is what differentiates a distinction student from like a B student. Okay, the planning of investigation. This is usually worth 4 to 6 marks, depending. Yeah, but it's usually worth quite a substantial amount of marks. Okay, so when you have your planning, they will tell you something like plan an investigation for this particular experiment. Okay, usually it's related to what you did before in your hands-on. So that usually the practical component is divided into two things. You do your thing, do. Then at the end, you need to do some planning for a similar experiment that what you did to what you just did. Okay, so how to do? You need to write a step-by-step description of the procedure for the investigation. You need to include a few things. The key variables, such as your independent change variable, your dependent, your measured variable, and your controlled variables for the given question. Right? This also means that you must write your hypothesis. Okay, so what must you have? Hypothesis, independent variable, dependent variable, controlled variable, okay, safety plan. Okay, the fifth one, safety plan, later I talk about it. Okay, so yeah, then you need to describe how do you actually measure the experiment, or how do you actually change the experiment? How do you keep things constant? For all of this, you must give real values. Don't just say I want to keep it the same. Like now, these two I make same. You must give a real value. For example, I will add equal 5. Okay, I will add 5 cm cube to 4 cm cube or something, and I will keep it equal for all experiments, for all the repetitions. So that you must state it, the actual number, and then you say that I keep it constant. Okay, it's a bit, I know it's a bit tall lah, like you have to keep repeating yourself over and over, but there's a lot of lines for this. It's like 10 lines or 20 lines for you to write on. Don't worry, you got enough space. Okay, anyway, you should then write how your data can be used in order to reach a conclusion. So you also need a conclusion. Okay, and then your risks. Okay, what are risks? Risks are things that could go wrong in the experiment. For example, if you're using visqueen tubing, you could say, oh, the visqueen tubing can tear. If you are doing something like maybe the plant, then maybe the plant might lack water and then wither or die, that kind of thing. Okay, and then how to keep the risk to a minimum. Okay, so then you must actually evaluate your investigation, such as identifying experimental errors and limitations and how they affect the results, and some modifications or some comments. Okay, this one is may or may not happen. This actually experimental errors quite likely to happen, but the bottom two not so common. Experimental errors though very common. Let's talk about that experimental error thing. Okay, I talk about it later. I talk about this first. Okay, this is almost the end already. Okay, let's talk about these two words called reliability and accuracy. Reliability is a metric that determines how closely repeated measurements match up and can be used to apply to a single measurement or the entire experiment. A measurement can be repeated and the differences in the results can be compared. If the same result is obtained when a measurement is repeated, it's considered as a reliable. In a similar fashion, the reliability of an experiment's results can be verified by repeating the experiment and comparing the differences in results. If the same results are obtained after repeating the entire experiment, the results are considered reliable. Okay, so let's see what's reliable. Where's my reliable? Not this one. Okay, reliable is something like this. Okay, the dots are very close to each other. Okay, this one later is about accuracy. So reliability means that if you throw on a target ball, right, it must always be near to each other. Okay, whether or not it's really you hit the middle of the target ball, it's a different story. Okay, but if it's near to each other, that's why it's called as reliable. That means that your values don't deviate too far from each other. Okay, so how do you improve reliability? You can alter the experimental design and fix your control variables. Okay, or you can choose more appropriate apparatus. Okay, don't choose the thing that's too big or too small. Choose the appropriate apparatus, and this will limit the effects of random errors. Okay, later we talk about this kind of thing called random errors. Then, on the other hand, you can also improve the reliability of a whole experiment by making sure that your individual measurements are reliable, and also increasing the number of repetitions and taking the average measurement. Okay, so that is what I call as reliability. Okay, if you do it 3 times, not enough, you do it 5 times. 5 times not enough, do 7 times. Okay, usually in odd numbers lah. Okay, then the other thing is called accuracy. What is accuracy? It's a measurement of how close the data or observation is from the actual value. Okay, in simpler terms, it means the quality of the results. Okay, so you see, that means that if I'm weighing a 100 grams object, I know this object is 100 grams. Then the machine must tell me 100 grams. Don't tell me 101 or 199. That kind of thing they're not accurate anymore. Okay, so even though the machine can be reliable, you can repeat the experiment many times, but if the machine is not accurate, then the whole experiment will mess up already. Okay, so the accuracy of the data depends on the experimental techniques and the number of errors. It can be improved by eliminating or minimizing errors. We will talk about that soon. Ideally, the results obtained should be both reliable and accurate. However, you may obtain results that are reliable but not accurate. Okay, so why? This is a good experiment. You did everything perfect. Your control variables, your constants, all this, all sweet, then it's all perfect. Okay, but in science, nothing goes to plan. So usually this is what you actually get when in real life science. You will get things that are reliable but not that accurate. Maybe just a little bit far or very far. It could depend. Okay, why? Because there are certain errors that people can make. So let's talk about these errors. Okay, this thing called experimental errors, you must be aware. Please highlight, circle it, or star this table. Experimental errors are errors that are inherent in the process of taking experimental readings. Okay, the word inherent means that it's natural, like it's part of the process. You can't avoid one. Right? And you can't simply eliminate it by repeating the experiment, no matter how carefully. But there are certain ways that you can minimize it. Okay, so what's an example? Okay, so for example, you want to do an experiment on yeast, biological specimen, but each packet of yeast can be different from the next packet of yeast. Okay, it depends on the manufacturer, it depends on certain conditions, the weather, everything. So you got so many different things. This is what I call as experimental error. You cannot control it. I can't go to the factory and fix it for them. I can't change the weather. So these are beyond my control. So these things like biological specimen not consistent, the limitation of instrument use, for example, a lack of precision. Okay, actually this one must be careful. Okay, don't use instruments that are going to be not precise. So this is what I would call this as a instrument precision error. Okay, so if they ask you for a source of error like that, what they ask me the question say, tell me 2 sources of error in this experiment. You can say there is an instrument precision error because the instrument is not precise enough to measure small volumes. So how to avoid? Use a more precise instrument. For example, a burette. A burette is similar to your dropper, like that thing you suck up the liquid one, right? But it's more precise. That means you actually can tell what's the volume. Dropper you just anyhow press and some volume come out. Okay, so it's not dropper not very good. Or even syringe not the best, right? Burette is actually very, very accurate. All the way until like 0.1 cm cube, something like that. Okay, so there's another kind of error, which is called called mistakes. Okay, mistakes. So they are not the same as experimental error. What are mistakes? Mistakes are reading the instrument wrongly. These are what I call as human mistakes, or just messing something up. Yeah. Okay, so one example is reading the instrument wrongly. For example, you never read the meniscus. You never move your eye down to the meniscus line. So you got parallax error on your measuring cylinder. Or you careless, you never read the instruction, you mess up the steps, right? You skip one whole step or you skip one whole page, then you end up the whole experiment explode. Okay, so let's look at some sources of error, which are sources of experimental errors over here. First one is very common, right? It's also commonly tested. It's called the instrument is not precise enough to measure small volumes. So how to reduce? Use a more precise instrument. For example, a burette, or if you are doing the math or something, use a more precise measure electronic balance. Then the sample size too small. So for example, you do potato, you only do 1 potato for 1 concentration. That's too small already. Sample size too small. You need at least 3 for each concentration. So increase the sample size. Then the intervals of temperature, pH or concentration are too large. So for example, you want to test a certain thing, but you use the temperature like 0, 20, 40, 60, 80, 100. Then like the scale is so big, it's too crazy already. Okay, but if you actually know this experiment only needs to be like from maybe 20 to 30, then you just 20, 22, 24, 26, 28, 30. Okay, that kind of more accurate, right? Smaller intervals of this temperature, pH, or concentration. Okay, so you can actually see the relationship for the variable more accurately. Okay, lastly, difficulty detecting color changes. This mainly happens in your Burette test, alright, a Benedict test, that kind of thing. Use a colorimeter if available. If not, no choice, right? Just write what you see. Okay, and with that, we come to the end of this practical skill session. Alright, I will show you one example using, I think, the 2022 pure bio practical paper. It's applicable for combined also, so just stick around and listen for that. Okay, alright, so that's it for now. It's me, I'm signing out.